Welcome, geniuses. I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Our next question, they give you the length, alright, and value E, alright, then they said they're going to use the same steel, twice the length and half the diameter. What will be the Young modulus? Actually, this question is a trick question, because if you are using steel for the first case and you are using another wire of the same steel, it would mean the Young modulus is the same. So originally is E, so therefore this is also E. Now if you attempted to calculate, you wouldn't be able to, because nothing is mentioned about the force. So there's actually insufficient information to calculate if you wanted to. Now this question, they gave you a large crane, alright, on the construction site. So basically this is only a model, alright, and the material used for each part is the same as in the full size, alright, in everything, the cable and the load as well. So the model is 1/10 full size in all linear dimensions. So what is the ratio of stress in the full-size crane over the stress on the model crane? Now remember, we have two choices. You can either use stress equals to force divided by area, or we can actually use the formula for Young modulus. But since we can calculate the force in the area directly, we don't have to use the Young modulus and extension. I will not use that, alright, because there'll be too many variables. So we try this first. If we can't, then only we try the Young modulus. So let's try the stress equals to force divided by area first. Now, because the force on the cable is actually due to the load, we can call the load here mg. That's the force on the cable. Area will be pi over 4d squared. Now, how would I actually convert to all the linear dimensions here? So linear dimensions basically means that any measurements in terms of like centimeter or meter, right, there's linear dimensions. So millimeter squared, meter squared, all these are non-linear dimensions. So everything is in linear. So therefore, if the load in the model will obviously be smaller than the load in the full size. So they told me that the load here is a cube-shaped load. So assuming it's cube-shaped and the sides are y, then your y cube would give me the volume, and y by itself is actually a linear dimension. So what I would do is I will change mass to linear dimension by taking density times the volume, which is y cube. So y here is a linear dimension, so we can use y cube here. So g remains as a constant, pi over 4 is constant. Now diameter by itself is also a linear dimension, so we don't have to change. So don't worry about the function. As long as the quantity like y and d are linear dimensions, then we are okay to go. So the ratio of the stress in the full size to the model, we can actually use this ratio. So the density, pi over 4 and g are constant, so no need to write. So it will be y cubed over d squared for the full size divided by y cubed over d squared for the model. So therefore, by cross multiplying, and that means you will do inverse this, and grouping them together, you get y of full size over y of model cube, and then you will also get diameter of model over diameter of full size squared. Now, the long way to do would be to take the ratio, right, that the full size is bigger than the model by 10 times, then you cube it, and then the model is smaller than the full size by 1/10, then you square it, and then you get 10. Now in this question, which is similar to the previous one we discussed, again you have a large crane, right, a cube-shaped load, alright. Basically everything is the same as before, where the model is 1/10 of the full size in all linear dimensions, but this time they want to find the extension. So to find the extension, of course the easiest would be to use strain, where strain equals to ratio of extension to original length. But in this case we don't know the strain, so we have no choice but to use the actual formula for Young modulus. So and the actual formula for Young modulus will be E equals to FL over AX. But since we want to find extension, I'm going to make X as a subject, so I will get this equation out. So then I would change the force, which is the load on the cable, to the weight of the load. So to find the weight of the load, I will change it to mg. where the m I will change to density times volume of the cube, which is y cube, because I want linear dimensions. L is already a linear dimension, don't need to change. Area will change to pi over 4 d squared because diameter is a linear dimension. So right now we have y, L, and d which are linear dimensions. So density, g, pi over 4, and e are constants because it's the same material. So we can use the ratio again. So whereby if you're using the ratio, it will be x2 over x1 will be y2 cubed L2 over D2 squared divided by y1 cubed L1 over D1 squared. So cross multiplying, you get y2 over y1 cubed times L2 over L1 times D1 squared over D2 squared. So in this case here, you will get, now y2 is actually the full size, so that is 10 times greater. L2 is also the full size, so over the model is 10 times, but D1 over D2 will be 1 over 10 squared. So in the end, you will get 10 to the power of 2. In this question, they are actually joining a glass reinforced plastic rod to a nylon rod, so this is joined together here. Now they gave you the same cross section and same length, but the Young modulus is different though. Alright, and the composite rod here, which is the combination here, will break when the total extension is 3 mm. So what's the greatest stress that can be applied? So let's start off with the formula first, which is Young modulus is ratio of stress to strain. So your stress will be Young modulus times strain. Now we have to break down the strain though to extension over original length, because they mentioned about the total extension here. Now you must understand that when you apply the force, even though the forces will definitely be the same on both sides, but the extension in the plastic and nylon would be different. Why would they be different? Because of the different Young modulus. So same force, but different Young modulus will give you different extension. So basically, to find the extension of the rod, alright, we have to find separately the plastic and the nylon. So what I'm going to do is I'm just going to write down any equations that I know. For example, I know the total extension is 3, so extension of plastic plus extension of nylon is 3. So therefore, we also have another formula that we can use, which is the ratio of the extension will be the inverse ratio of the Young modulus. Now, in case you're wondering how I got this formula, you can actually figure it out from the formula that we always use, which is x equals to FL over A times Young modulus. So since area is the same, F is the same, L is the same, so x will be inversely proportional to the Young modulus. So therefore, what you will have is the extension of nylon over the extension of plastic will be equals to the inverse ratio of the Young modulus, which is Young modulus of plastic over nylon. So Young modulus of plastic is 40, Young modulus of nylon is 2. Alright, so you bring the extension of plastic over, so you have a second equation. So now we have two equations here. We can actually solve simultaneously. So substitute the extension of nylon as 20 xp here, alright, into this part. So you get xp plus 20 xp, and then finally you get the extension of plastic. And then the next part, since we already know that the formula for stress is Young modulus times extension over length, now we can use it for plastic. It will be the same as nylon because they're same force and same area. So Young modulus for plastic is given as 40 gigapascal. And now you know the extension is 1.43 times 10 to the power negative 4, and the original length is 1. So you calculate, you will get 5.72 times 10 to the power 6, which is C. Now in this question, we have a hollow tube, and the tube is under tension, alright, with the two forces here, T and T. So to reduce the stress, we want to thicken the wall. So the tube diameter and the tension are the same, alright, you want to keep that constant. So what wall thickness will give half the stress? So let's start off with the formula for stress, which is F divided by A. So the F is obviously your tension, so you don't have to take two of them times 2, right, because just one of them is enough. Because it's impossible to stretch if you apply one side, then you will just accelerate to this side. to this in this direction. So you have to apply equal and opposite forces for them not to move, to stretch. So the force here is just 1. Alright, no need to times 2. So the force here is the T. Area now. The area of a hollow cylinder, which is the area of the material inside here. Alright, in the wall here. How do I find this area here? So you can take the circumference times the thickness of the wall. So the circumference is 2 pi r and the thickness is W here. So that's my formula. So making W as the subject, because I need to find the wall thickness, so you get W is T over 2 pi r times sigma. So what I did was I changed the 2 pi r to pi d, because 2 pi r is the circumference, pi d is the same as circumference, because 2 times r is your d. Now why I want to put it in terms of the diameter, because what they told me is that the diameter is constant. But if you don't want to, it's fine, right? You can leave it 2 pi r or pi d, doesn't matter, because that is not a factor for us. Now anyhow, these 3 are constants, and your W will be inversely proportional to your stress. So what we want to do is to find the new thickness. So W2 over W1, use the ratio method, equals to sigma 1 over sigma 2. So since you want to reduce the stress, let's say original stress is sigma, to half of it, so half sigma, so you get 1 over half. So then you times the W1, which is W, you'll get 2W. Alright, so answer is C.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with 1 or 2 past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.